Hello, and welcome to part 2 of the 1503 TDR, or time domain reflectometer repair. And this will be the final one. This unit's up and working now. When we talked about the battery in the first video, I mentioned to make sure absolutely positively that if you have one of these built, to tell either Batteries Plus or whoever's building it for you, do not glue the cells together. They need to float back and forth to fit into this properly so that this case won't bind inside the case of the TDR unit. What I neglected to mention was, before you attempt to rebuild this or especially put it back together with new cells, have the fuse out of it first of all. But that's not going to save you from utter destruction if you're not careful. Right here is the positive connection, the red wire positive connection, which you can see through the top here. Before you do anything, take the fuse out, touch that with your soldering iron, and pop that wire out the back. Pull it up so that it's outside of the case, because as soon as you loosen these 4 screws here, this little metal frame that's inside the back of the unit right here, this is a little square frame that fits around the circuit board in the back. And I promise you, you cannot get this apart without this falling down across the terminals inside. And if your batteries have any kind of a charge in them, the old one, you're going to get sparks. The new one, if it happens, you're likely to burn up the wire, or, burn up your batteries, whatever. There's plenty of room after this whole pack is reassembled, and this is no longer in danger of shorting anything, because once it's screwed into place, it's clear of all the terminals. But as soon as you take the screws out, I guarantee it's going to bridge these 2 contacts in the back. There's just no way to avoid it. But anyway, once all the screws are in and the pack's physically assembled, you can easily slip that wire in the back, in here. There's plenty of room. And then solder it on the front, and you won't have any problems. Then slip your fuse back in, and you'll be in business. Plug it in for 24 hours and let it charge, because this unit has to have a charged battery to operate. It will not operate on AC power by itself, and it's going to struggle to charge the battery and operate without, unless the battery's fully charged. The charging circuit in this is barely a trickle charge, because it's designed to be plugged in and forgotten about until the unit's needed. And it will not carry the unit. Now, plugged in with the battery in it, you'll get quite a few hours out of the unit. But they tell you, if you want to use it for benchtop operation, continuously, to buy the 12-volt power supply that replaces this unit. So this is designed only to trickle charge, and it will not carry the battery for more than 6 or 7 hours plugged in. About 5 hours continuous on just the battery pack. So we're going to reinstall the battery pack. Oh, another thing. One of the viewers last time contacted me and said the easiest way to get this out of the case, and shame on me for not figuring it out, back the screws out most of the way, because these are captive screws, but you'll want to back them out part of the way, leave the threads partially engaged, probably back them out half the thickness of the head on all 4 screws. Stand it up on its back like this, and merely push down on the case, and that will pop. Well, you can't see it now. That will cause the front of the unit to pop out when you press down on the case. Easiest way to get it. This unit is designed to be waterproof. Putting a screwdriver in here like I did, you chance damaging either the edge of the plastic case or the rubber gasket that's behind it. Now, I did neither, but I was being quite careful. This unit actually is designed, let me tighten that screw before I forget. This unit is actually what they consider waterproof. You can use this in the pouring rain outside. And in fact, one guy contacted me and said he's seen this thrown in a kiddie wading pool, taken back out and used. All of the knobs, all of the controls have gaskets behind them. The BNC connector does. There's rubber gaskets all around the CRT bezel. Everything on this is sealed and supposedly watertight. Now, you got to remember, this is 1980s. Is the grease on the O-ring still viable? Is the rubber on all the O-rings still viable? I wouldn't throw this in the pool. But I certainly wouldn't worry too much about taking it out on a, partially rainy day and getting light rain spatter on it. It's not going to hurt it. I wouldn't submerge it, but again, I wouldn't worry about rain spatter. Okay, let me get the battery installed, and we'll give you a quick rundown. I hate that, on how this thing works. Let's see here. That's up, yeah. There. Battery pack slid right in. A little bit snug, but perfectly acceptable. We'll snug up these two screws. And again, the battery pack has its own gasket, and it is completely isolated internally. Even if the water was to leak in here, it won't leak into the scope. But there are seals. There's seals on the screw heads. There's seals behind. This whole thing is just designed to be as waterproof as you can get it. And you probably saw the desiccant container in the first video. It wasn't pink paint yet, but it had gone away from blue and was on its way to turning pink. And again, 1980s. This thing's been, around for how long? So I took the desiccant container and put it in the oven. We let it sit in the oven for about an hour and a half, hour and 45 minutes at 225 degrees. And it turned nice and blue again. Recharged, ready to go and pull any humidity that happens to be left inside the case after I've closed it up. The desiccant, they recommend above 212, which is the boiling point of water, and below 260. Don't exceed 260 for the silica gel desiccant. I figured 225 was a good safe number, and after an hour and 45 minutes or however long it was in the oven, I put it in there before I started dinner. Just let it cook the whole time I was having dinner, and watched a couple YouTube videos, and then took it out, and it turned blue again. So everything's good to go there. Now, operational. We've got the manual, and it turns out I was wrong. I did have the right manual, and I didn't even know it. What I have here was the last iteration of this unit. The original unit had two push buttons here and a screwdriver adjustment potentiometer similar to this one. And they were labeled solid poly and foam dielectric to compensate for the velocity factor of different coaxes. Evidently that didn't cover enough of a range. Now what they probably did, whoever was using this, whether it was AT&T or whoever happened to be operating the unit, they probably only used one type of coax. Their calibration people probably set it up and adjusted that trim pot for whatever type of coax they used, and that would have been the end of it. They may have had people complain about, I think the original unit only had 50 and 75 ohms. This one has 93 and 125 ohms as well. But these were an upgrade before they went to the newest unit, which has a much bigger CRT and is completely different looking. And they tell you to adjust this to compensate for velocity factor. However, they don't tell you what the settings are. And I'm sure it varies from unit to unit. So what you need to do is take a length of your favorite coax. Let's say you were getting ready to go to the flea market and you were looking for RG8, LM400, and 9913 cables. Well, you'd look up their velocity factors, and if you had one around and it happens to be 9913 is 85%. I don't know if you can see that. 85% velocity factor. So you take a known length of it. In my case, I have a 39.5 foot, basically 40 feet, 39.5 foot section of 9913F. I use that to calibrate it. Now, for a little more accuracy, you probably want to go out to 100 foot. But you take a known measured length of coaxial cable, and I'll take my known length here of 39.5 feet of 9913F, which has a published velocity factor of 85%. Now, knowing that this is basically 40 feet, I plug it into the unit. I've got this on 0.5 times 10, so it's 5 feet per division. Set my first indicator. I hope this is clear on the video. Yeah, I can see it strobing. There's not much I can do about it. My beginning of my peak goes on this indicator over here. I'm at 5 feet per division. So 5, 10, 15, 20, 25, 30, 35, and it ends up at 39 and almost a half. This thing is almost perfect. Now, a word of warning, this thing drifts. And it's already moved over. There we go. It's sitting right at 39 and a half. And I did that by adjusting my distance calibration to my known length. By changing this knob, you can see now it's only 35, 6, 7. It's only reading 37 feet. So once I've calibrated this, 1, 2, let's see, it's going to go. It's supposed to be 0.08, so 10, 9, 8. I came up with those numbers because now it's exactly at 39 and a half feet is what's reading on the screen. Now I can, with confidence, go to the flea market, and if somebody has a spool of unknown length of 9913 that I want to buy, I can plug it into the unit, and if it doesn't have an end on it, I can strip off a little bit of insulation, and you can either use the binding post setup or a couple of alligator clips plugged in. That'll go on. This adapter goes right into the BNC, and you could clip onto the shield and the center conductor. This little bit of length isn't going to make any difference. It's not that critical. And you'll be able to determine how much coax is sitting on the spool that you buy. And what did I do? I hit something. There we go. Click. Alrighty. So that's for a good piece of coax. Let me get trot down the other end of the room and get the other end of this piece of coax. This is showing you an open coax. You get two positive going peaks. You get the pulse going out and the pulse being returned. If you have a coil of coax that has a short in it, what did I do with my shorting there? There we go. What you'll see is an inverted return pulse. That shows a shorted coax. Now your return pulse is going to be slightly lower than the pulse going out. That's going to be determined by how lossy the particular coax is, and if you had 500 feet of it, you could do the calculation. You know, the published return loss, you can figure out how many dB down the return should be over, say, 500 feet by looking at the published losses on the coax, and gives you a good idea of the coax being in good shape. If the coax has been sitting out in the rain, you're not going to get much of a return signal. It'll be very lossy. In fact, I could probably duplicate. I'm going to pinch this with my fingers. If you had that type of return on a 40-foot length of coax, I'd bypass it. It's probably contaminated. But that's about 85–90% of the power of the signal coming back, so it's not losing much power on a return trip. But if I was seeing, wet my fingers, that type of a return, I'd be kind of concerned that the coax was probably gone. This isn't going to be 100% accurate, but it's going to be a good indicator of the condition of the coax. And again, if there's a short somewhere in the spool, you're going to see that on the return instead of a positive going pulse. And all I've got on here is an adapter, SO239 to BNC, so I can plug in the PL259. So that's with a 50 ohm cable with an 85% velocity factor. Now, oh, I had a piece of cable here, another one. Let me find my other piece of cable for a demo. Okay, we have a length of RG58C/U, which is 50 ohm, 66% velocity factor, and this measures exactly 10 feet 3 inches. And the published velocity factor on this is again 66% versus the 85% of the 9913. So I am going to go to, we're still on 1/2 foot per division. I'm going to move this over to the start point. Now I have to adjust the velocity factor for this coax. So I have my lookup table. You're going to want to calibrate your unit before you went to the flea market, so you're calibrated, or you have a lookup table for your coax. This is going to be 0.3, 0.1. This is labeled 0.2 up to up to 0.9, and this one's 0.00 up to 0.10. So I want 0.3, 0.10. So I'm going to go 0.3, 0.10. Now, when I align over here at my start point, this is 5 feet, 10 feet. So if I went out and I was looking for RG58CU and somebody had a coil of it and say I needed 150 feet, I could hook up to the coil, and if it only measured 90 feet, it's not going to do me any good. If it measures 160 feet, I know I'm fine. The longer the piece of cable you use to make your initial calibration, the more accurate it's going to be in the field. Calibrating it with a 10-foot piece of coax, I wouldn't feel very comfortable trying to measure 500 feet. It's going to be off, you know, a fair percentage. Maybe I could be off 10 or 15 feet or more. But I'm never going to use RG58U for more than jumpers 10, 12 feet. Certainly I'm not going to go more than 15 feet. The stuff is just too lossy. I just use it around the shack for jumpers and for testing purposes. So I wouldn't be, you know, I wouldn't care if I was off 10 feet buying a coil of this stuff in the field. 10-foot calibration length is fine. But if I was doing a serious search for LMR 400 or 9913, I'd want to take, you know, 75, 80, 100 feet measured piece and use that for my velocity factor setup. They don't give you a chart in the book that it tells you it's for velocity factor, and it tells you how to adjust it, but it doesn't give you a lookup table, because these units are probably going to vary unit to unit. And even if I went through the full calibration of the unit, it's going to drift over time. The easiest thing to do is, before you head out, do a quick check with some known pieces of coax you have, and you'll have a lookup table you can take with you. Or if you're only looking for one particular cable, you just preset this before you head out to the field and you're good to go. Now, this is my feet per division times 10 times 100. This is also feet. If you were measuring 1,500, 2,000 feet of cable, then this would come into play. And once you've dialed it in, you push this button to make sure you're still sitting on 0 and measure how many feet you have. But I'm never going to measure anything of that length. It's silly for me to try to measure anything that long. Your typical ham, you're probably never going to go over 500 feet with a length of coax. If you're going over 500 feet, you're going to be using hardline, you know, you're starting a whole different ball of wax there. Now this will measure hardline, certainly will measure hardline once you know the velocity factor and you've calibrated it against a known length of hardline. However, your typical ham probably will never exceed 150 feet with a length of coax. Typical. I know somebody's going to say, oh, my setup's 225. I really don't care. You're going to have enough distance calibrate, or enough distance range on this knob. You'll probably never get into that one. And that's just for great distances. This will go out to several kilometers of, you know, different types of cable. By the way, you can measure the lengths of things like network cable or twisted pair, many different types of cable. But to do that, you need the adapters. There's adapters that go on here to have matching transformers, and I don't have them. They didn't come with the unit. I have no use for them. I'm not measuring 1,500 foot lengths of data cable. But I could certainly do it with any type of coax. And as a matter of fact, let's take a look. Let me find one more. We have a coil, unknown length of cable TV, and this is F as in Foxtrot 6 Sam Victor Victor, F6 SSVV. And I looked up the specs on this. This is, again, 85% velocity factor, so I'm going to go to 0.5, 2, 3, 4, 5, and 0.08, 1, 2. I have a BNC to F adapter that I simply put on the front of the unit. Actually, I'll put it on the coax first. Am I in frame? Yes, we're in frame. We will thread this on here, and this is going to be somewhere between 30 and 50. I don't really know what it is. And it's 75 ohm cable. And why am I not getting the right return here? Why is it acting like a shorted cable? Operator headspace, folks. Operator headspace. What happened was, when I went from this setting to the 0.5, 2, 3, 4, 5, this is my return pulse. There's my send pulse. I've got to remember every time, when you change this setting, it spreads the pulses out. And this one went off the screen. I was thinking this was the pulse going out, and that's why I was confused. Again, operator error. Brand new piece of equipment, and my first time playing with it now that it's up and functional. You're seeing it live. Okay, we are on 0.5 times 10. Oops, I had that knob moved. Let's get it better. This, again, does the same, you know, it spreads out the distance, so. Okay, 0.5 times 10, that's on 0. We're on 75 ohms instead of 50 ohms. 5, 10, 15, 20, 25, 30, 35, 36, 37, 38 feet. 30, no, 35, 6, 7, 39 feet. So basically a 40-foot piece of cable is what's here. Again, this thing's not going to be 100% accurate using a short piece of cable as a calibrator. This was calibrated with a 10-foot piece of cable. So how close is it? Who knows? If I had a 100-foot coil of this, I'd calibrate it with a 100-foot coil. But close enough for field work, for running out and buying a hunk of cable. One more thing I should mention. And I'm going to set this back to 85% velocity factor, or no, excuse me, 66% velocity factor, 0.3, 0.1. So we're going to go 0.3, 0.1. There's my out pulse. Here's my short piece of cable, because I know somebody is going to ask me, can I use this thing to look at my antenna, measure my coax up to my antenna? Probably not. And the reason being, you see there's a return pulse from an open-ended cable. And if I can get the short to fall where I want it to. Come on, short circuit for me, baby. Can't get it down there. Maybe I can with this. Oh, 50 ohm cable. There we go. Okay, that's a shorted cable. That's an open cable. If you put 50 ohms, if you put an antenna on the other end, a termination like an antenna that's matched impedance, you don't get a return signal, because all of the energy gets used up by your load, as it should. That would be a 1.1 VSWR. That means all of the energy that you're transmitting down the line is being consumed. Now, if your antenna is horrible, you might get some return. But if I try to connect this to my my beam, which is a 5-band beam, it covers 10, 12, 15, 20, 10, 12, 15, 17, and 20 meters. All you get is a bunch of squiggles. You get all kinds of reflections coming back, and you can't even determine which signal's the real one. I just did it for giggles. I didn't think it was going to work, but I tried it. But if you have a good match on your antenna, on a monobander, you're not going to get any return signal at all. That might be a good way to say, well, the antenna's connected and it seems okay, I guess, but that's not a guarantee. But again, if you have an open up at your antenna, if something's broken, you're going to get that kind of a return. And if you know how long your cable is and you're getting that signal coming back, then you say, you know, you got a bad connection on the antenna. That would be a dead short on the other end. That would be an open on the other end. And that would be a well terminated antenna. It won't give you a length, but if you know what the length is and you know it falls in the screen, you can probably say with a fair amount of confidence. Of course, you're going to get that with an SWR meter anyway. So, enough about that. This thing will go into my stack of equipment. Goes to the flea markets if and when they open again. Hopefully this vaccine that they have been talking about will turn out to be the real deal, and by sometime next year they'll have distributed it around. I am still stuck here in the United States. I can't go back to my second home in Thailand. Well, I can, but it's an expensive proposition. They want you to spend 2 weeks in quarantine in a specially certified hotel, and what they do is they put plastic on the furniture and on the carpet, and you're only allowed out of your room 1 hour a day to go up on the roof to the pool. You know they're going to be charging through the nose for that. And then you have another week you have to stay in the city while they monitor you. So it is simply not practical to go back at this point in time. This being November, what the heck's the day? 15, 14, I don't even know what the date is today. That happens when you retire. Today is the 15th, November 15, 2020. The world as it is. So that's it. We have a working TDR for the cost basically of a battery pack, refreshing the desiccant. Oh, I had a bad connection on the back of the BNC connector, which was making the unit intermittent. At first I thought the BNC connector was bad. Turned out to be the solder joint where it connected to the board had gone sour. So we resoldered the BNC connector, we put a fresh battery pack in it, and that was about all this thing needed. That was a good buy. Now I have a working TDR that I can take in the field with me. Hope somebody found this useful, and let me know in the comments if you did. If you need to know more about the unit, buy the book. The book isn't real helpful. You're kind of going to have to figure some stuff out on your own, like I had to come up with my own lookup table here, and no, me making a lookup table for you won't work. Your unit's going to vary slightly different from mine. Oh, and this thing drifts. The time base drifts over time. So you want this thing on for a couple of minutes, but just in the time we've been talking here, this has been slowly moving over to the edge. This unit, again, it wasn't meant to measure down to an inch. If they had 5,000 feet of cable and there was a fault, and this told them the fault was at 3,500 feet, what I would do is go to the other end of the cable and measure back. I should see a 500-foot fault. It's going to give you a pretty good idea of where to look instead of having to examine all 5,000 feet. They would jump in the truck, drive from pole to pole until they'd gone out about 4,500 feet, look for the fault. Okay, what follows is a concept video. The purists out there who are warming up their keyboards to start screaming about the numbers I'm about to give are unrealistic, go find something else to watch. This is for people who don't understand the concept of velocity factor and just want to grasp what I'm talking about, the basic concepts. Now, if you look up the speed of a radio wave or light, which is basically just another electromagnetic form, radiation form, the speeds are listed as 186,282 miles per second, or 299,792 kilometers per second. And that's typically rounded off to 187,000 miles and 300,000 kilometers. Then we'd have to start talking about milliseconds and microseconds and nanoseconds. We're going to throw all of that away, and we're going to use made-up numbers just to make this as simple a concept as possible. All right, we're going to assume that in free space, in other words, just out in the open in space, a radio wave will travel 100 feet in 1 second, just to keep the math simple, 101. Now, velocity factor comes in when we have an 85% velocity factor coax. That means in that same 1 second time, the signal will only travel 85 feet. Now, if it gets reflected back, that's 2 seconds round trip. 1 second out to go 100 feet, 1 second to come back. In the 85% coax, same thing's going to happen. 1 second out, only 85 feet, because the insulator or the dielectric in the coax slows the propagation of the wavefront down. So it'd be 1 second out, 1 second back over 85 feet instead of 100 feet. 66% velocity, it's going to go 66 feet in a second, come back another 66 feet in 1 second. That means that on our display we have a fixed, let's say we have a fixed sweep time on the scope. In other words, from the start, when the trace begins, to the end, this is a constant. It's always moving at the same rate. Let's say it takes this many divisions, 1 second, 2 seconds, because remember, we're going out, it's reflecting, and it's coming back from an open coax on the end. So, and we always measure from the beginning of the pulse. That's why these are offset. We always measure from the beginning. This corner right here gives us the sharpest indication of the start of the pulse, and if I had the coax hooked up, we'd have a second one over here, and we go from that same excuse me, position. Alrighty, so now we know it takes 1 second out, 1 second back. This is our 2 second sweep, tells us this is 100 feet of distance. If we connect this up, it's the same 1 second out and 1 second back. If we maintain that same sweep rate, we're going to think we have 100 feet of coax, when actually we only have 85 feet of coax. So these two knobs will adjust the sweep rate to compensate for the velocity factor. And that's why I used a known length of coax at 85% velocity factor. And I used this to adjust the sweep rate so that the start and stop points accurately measured my 85 feet. And I did the same thing with the 66% coax. So then when I hook up any coax with an 85% velocity factor, the sweep rate will be accurately calibrated so that it shows the correct length on the screen. By changing the sweep rate, I will end up with a trace that ends here, because the time of the trace will be slowed down so that it takes a little bit longer, so that that 2-second point falls here instead of out here, and accurately reflects the length of the coax. Okay? Same thing on the 66% velocity one. We change the sweep rate to reflect the fact that this is only 66% of the speed of this one. And it's that simple. And I know the purists out there right now are screaming, oh, you should be telling about, you know, microseconds and nanoseconds. No. This is the concept. This is what these two knobs are all about, and that's why you take a known length of coax with a published velocity factor of a certain number, and I use that to calibrate these two knobs so that when I hook up another length of 85% velocity factor, I will get an accurate reading on the scope. Hope that was clear. Hope that helps. See you next time. I'm the Radio Mechanic.